Okay, so this is a question that maybe you've never considered before, but it's actually sort of an interesting conversation. Um, why? Why binary? Why do computers use base 2 for storing information? If you look at the history of computing, the different kinds of computing devices that we've created over the last 100 years, let's say, in general, information has been represented and fed into those computers using two states. Okay, so like early computers that used vacuum tubes, right? The tube was either on or off, right? Those were the only two states that a single tube could be in. We had mechanical relay-based computers, right? The relay was either open or closed. Uh, you would, give information in punch cards, right? The hole could either be punched or not punched. Um, some of you, I don't know whether you all have heard of core memory. It's an old way of storing information with magnets. The magnet could either have a positive or a negative polarity. And obviously modern computers use transistors, voltage high, voltage low, right? So throughout the history of computing, you've basically had two states to play around with. And so it is natural for computers to use binary data, on or off, right? A one or a zero. Um, Interestingly, of course, humans, we tend to be base 10 creatures. Um, some of the early computers used what was called a binary coded decimal, BCD encoding, where they would, the computer used bits, but the humans would put those bits into patterns that represented decimal digits, right? So rather than using a straight kind of base 2 encoding for numbers, the humans taught the computer to talk base 10, digits 0 through 9. Now, that encoding has, of course, fallen by the wayside. Um, and now we'll just use straight binary math for everything. I will say that the old BCD style encodings, because you were literally representing each digit in a number, it's actually a more precise way of representing, for example, decimal numbers, where the binary system for floating point numbers uses a approximation. With BCD, you can literally, have each digit explicitly. Um, but BCD turned out to be, kind of a hassle, and frankly, it wasted a lot of space. And so, most computers these days use true binary representations of numbers. And that's really what we're here to talk about. How computers encode binary, how you see it as somebody using the computer, and how you can encode and decode binary to decimal, right? A numbering system that makes sense to you, because that's, of course, what they taught you in grade school. Um, so let's talk about grade school, right? Come with me all the way back. And you had a decimal number, right? Like 1337 here, right? And in the earliest math that you did in grade school, right, you learned some basic facts. So that 7 at the end of the number, right, that's what we call the ones place, right? And then there's the tens place and the hundreds place. This is getting a little bit more advanced. First you were only doing single digit math, and then you moved up to 2 digits, right? And then, 4 digits and more. And so, thousands, hundreds, tens, and ones place, right? And, eventually you learn to add and subtract, carry numbers from one place to another, and multiply and divide and all that stuff. But this is kind of like the core knowledge. We're base 10 creatures. And, so the digits are in terms of multiples of 10, right? Ones, tens, hundreds, thousands. Now, from a math perspective, right, as a mathematician, what I would tell you is that thousands place, well, what's 1,000? 1,000 is 10 to the third. Hundreds is 10 to the second, right? 10 times 10. Tens place is 10 to the first, right? Just 110. And that ones place, well, the math people cheat a little bit. So 10 to the zero, you're like, 10 to the zero, what does that even mean? Okay, so like there's this secret, handshake where mathematicians have agreed that anything to the zero power is one, right? And they did that mostly because they needed it for this pattern, right? As you go through the digits, from right to left, the digits represent one more 10, right? So ones is 10 to the zero. The first, the rightmost three is 10 to the first, the tens place. The leftmost three is hundreds place, 10 to the second. The fourth digit there, the one, is the thousands place, 10 to the third. And you can keep going out like that as far as you want, right? The next place will be the 10,000s place and the 100,000s place. But you can see the exponents are going up as you move from right to left here. Okay? That's just the way numbers work for us human beings. Okay. Binary is a numbering scheme that, instead of using base 10, uses base 2, right? All we've got is two states, on or off. Right? But it follows the same pattern. So we've got a binary number here. Right? The digits can only be 1 or 0, 1, 0, 1, 1. Okay? But it follows the same pattern, just with a different base. Right? So that 1 all the way on the right here, okay, that's the ones place, right? I mean, 2 to the 0, right? So instead of 10 to the 0, this is now 2 to the 0. Binary is base 2, as we say, right? And so that makes this next position right here be 2 to the first. And then just following the pattern, right? The next digit over here is 2 to the second and 2 to the third, and so on. Okay. Now, 2 to the third is, sorry, we'll go from the other end. 2 to the 0 is 1, right? Anything to the 0 power is 1. 2 to the first is 2. So that's not the tens place anymore. That's the twos place. And the fours place. And the eights place. And so on, right? So instead of being multiplied by 10 as you move from right to the left, we're doubling. We're multiplying by 2 each time in base 2. Ones, twos, fours, eights, 16s, 32s, 64s, and so on. Okay? So this is how you work with different bases, but the pattern still applies, right? The exponents go up as you move from right to left, and you just keep multiplying by whatever the base is. Binary is base 2. Hexadecimal, which we'll talk about later, is base 16. And of course, we humans use base 10. So that's the basic idea. Now, how do we use that to decode a binary number? Okay. All right, so we want to convert this binary number that we just looked at, 1011, back to decimals so that we can, talk to humans about it. Okay, so here we go. That first one is in the eights place, right? We got ones, twos, fours, eights. Okay, so that first one is in the eights place. If it's a 1, it represents an 8. Okay, this next place, which would be the fours place, is a 0, right? So that represents a 0, regardless of the base, right? It would be a 0 in base 10, be a 0 in base 16. It's a 0 here. This next place is the twos place. So that's a 2. And then, of course, we've got a 1 here in the ones place. So that is a 1. Add them all up, right? 8 plus 2 plus 1, which is 11. You beat me to it. So this binary number, 1011, represents the decimal number 11. That's how this works. It's straightforward. You know, if there's a 1 there, it represents whatever number that position is, right? 8, 2, 1. Add them up, boom, get 11. That's the decimal representation. Now, of course, we don't tend to use 4-bit numbers in computers anymore, not for a long time. Most computers use at least byte-sized numbers. And a byte is 8 bits, okay? So 1s, 2s, 4s, 8s, 16s, 32s, 64s, 128s, okay? So 8 bits in a byte. And so when you write them all out like this, the largest bit is 128, and all the way down to 1. So if we wanted to convert this binary number into decimal, well, you'd probably pull out a calculator, wouldn't you? But we can do this manually. Okay, so 128 plus 32, 16, 8, 4, and 1. Let me show you a trick for adding these together really quickly, right? Look for collections of numbers that create a number that ends in 10. So for example, 128 plus 32, that's 160, right? Similarly, 16 plus 4 is 20. So 160 plus 20 gets you to 180. And all that's left over is the 8 and the 1. That's 9. And so the total of all of these numbers, I can do it in my head, is 189. Okay, so yeah, I mean, because these numbers tend to be powers of 2, there often are groupings. So for example, if this were 1 and this was a 64 here, you can put it together with the 16 and make 80, right? Or here we put the 128 and the 32 together to get 160. And so you can more quickly math up these things in your head if you don't have a calculator handy. Okay, so cool. For anything bigger than that, I think you're going to want to use a calculator. And I'll show you that a little bit later. But the first time around, it's useful to do this manually so you get a better feel for how these numbers sort of operate. Okay, so we can convert binary to decimal, but what about going the other way? What if you wanted to take a decimal number and write it as binary? So we're going to take 243 and we're going to convert it into binary in an 8-bit byte. Okay, so remember, 1s, 2s, 4s, 8s, 16s, 32s, 64s, 128s. Now, when you're manually converting a decimal number into binary, you want to go from the biggest numbers to the smallest, right? So we want to start over here on the left-hand side with the 128th place. And so the question we ask ourselves is 243 greater than or equal to 128? The answer, of course, is, well, yes, it is. Okay, so what do we do with that? Well, that means that there's a 128 in 243. So we put a 1 here in the 128th place. All right, so, but obviously 243 is bigger than 128, so there's going to be some left over, right? So subtracting 128 from 243 gives us a remainder of 115. I won't make you do that one in your head, okay? Okay, so we've got a 1 in the 128th place. We've got 115 left. And so now we move down to the 64's place. And we ask ourselves basically the same question. Is 115 greater than or equal to 64? Why, yes. Yes, it is. Okay, cool. So we drop a 1 into the 64's place. And then we figure out what's left over, right? So if you take away 64 from 115, what have you got? 51? I agree, right? 64 plus 51 is 115. All right, moving on. Same question, except now we're down to the 32s. Is 51 larger or equal to 32? Well, yes, yes it is. And so, boom, there's a 32 that we need as well, right? And then what's left over? 19, right? 32 plus 19 is 51. And we keep going. Next place is the 16's place. Is 19 greater than or equal to 16? Absolutely yes, right? So we drop a 1 into the 16's place. And what's left over? 3, right? Okay, so far, 128 plus 64 plus 32 plus 16, right? Well, that's 160 plus 80, 240. So we've taken up 240 of 243 with these 4 bits. And what's left over is 3. All right. Now we're down to the 8's place. Is 3 bigger than or equal to 8? Nope, it is not. So there are no 8's in 243. We put a 0 in the 8's place. What's left over? Still 3, because we haven't taken any more out. All right, down to the 4's place. Is 3 bigger than or equal to 4? Absolutely not. So we drop a 0 into the 4's place. What's left over? 3. Okay, moving on to the 2's. Is 3 bigger than or equal to 2? Absolutely. And so we drop a 1 into the 2's place. And what's left over is just 1. And so that 1 ends up in the 1's place. And there you go. This is the binary representation of 243. 111, 10, And you can do this, obviously with any size value, but honestly, once you get above, an 8-bit byte, it gets really tedious, really, really tedious. And so most, calculators, applications that you would find on your phone or on your laptop or, in Windows or whatever, give you, let me bring up the calculator here. Give you the easy way to convert between binary and hex and even octal. So this is just the Microsoft Windows calculator. It has multiple modes. There's the standard view, typical operations. There's scientific, which has all sorts of additional operations. But there's almost always a programmer mode, right? And so, for example, you'll notice here in programmer mode, there are different bases, right? So there's decimal, binary, and hexadecimal and octal, which we'll talk about later. So I'm here in decimal mode, and if I type in 243, you can see here that it's showing you what the binary representation is. If you click here, it will actually show you in the main number what the binary representation is. So if you want to convert from a decimal number to 243, decimal number 243 to binary, boom. All you got to do is type it into the calculator. You can switch and see what it is in binary. And that's particularly useful if you want to do a much bigger number like 243, right? You'd never want to do that by hand the way we just did it on the slide, but this is just a quick way of seeing what the number is in binary. But you can also go the other way, right? Like if I just picked a random binary number, 1 0 0 0 1 1 0 0 1 0 1 0 1 1 1 1, right? So that's 16 bits, which is way more than you'd want to do by hand. But now we can just flip into decimal mode, and you can easily see that that's decimal 36,015. By the way, I've been using the word bit. I probably should define it more explicitly. A bit is a binary digit, right? So a single 1 or 0 is a bit. We abbreviate that to bit just to make it easier to say. So when I say bit, I'm talking about a single binary digit. Anyway, your calculator can help you convert back and forth. But like I said, in this first exercise that we've got coming up, try and do it by hand just to kind of get a feel for these numbers. So we got a question in the Discord, and let me flip back to the slide the question is referring to so we can discuss it. Slide animation. Okay, so the question is about this slide where I was explaining kind of grouping things together that end in something that ends in a 0, right? And this is just a little trick that I learned at some point for adding up large groups of numbers quickly. The trick is to kind of cluster things together into values that end in a 0 and then add those chunks together. So as I was pointing out, 128 and 32 fit nicely together because they add up to 160. Similarly, the 16 and the 4 group nicely together because they add up to 20. And it's easier to do 160 plus 20 in your head, right? 160 plus 20. Well, it's 16 plus 2 kind of, right? So 180. And then whatever random numbers are left over, in this case the 8 and the 1, that's a 9. So the answer is 189. I think that's easier than, say, like what you did in grade school, where you stack these numbers up on top of each other, and then you just go down each column, adding the numbers together. That's kind of more laborious than chunking them up into groups and then adding the groups together. But grouping things into things that end in a 0 make it more easy to add the groups together. So yeah, so 128 plus 32, 160, 16 plus 4 is 20. 160 plus 20 is 180. Plus 8 plus 1, 189. And I'm able to do that in my head much faster than doing it pencil and paper. So that's the idea. Okay, so here's the GitHub with the PDF for the course and the exercises. Hopefully you were able to download those exercises. Let me go ahead and open those up. The exercises are also Creative Commons licensed, by the way. So the exercises are here in this PDF. And there's going to be 5 different exercises for the 5 sections of this course. So we got some questions. I want you to translate these binary numbers into decimal. Then I want you to go the other way and translate some decimal numbers into binary. And then we're going to have a little bit of fun with ASCII encoding. And you can decode the secret message using this ASCII table. So those are the questions, that you'll be working on for the next little bit. And then after that, I've provided the answers. Right after the questions comes the answers, right? So I'll show you what the answers are. So if you get stuck and you want to peek, the answers come right after each section of questions. So I want you to go ahead and work on your own and work on these first few questions. Somebody in Discord asked to see the answers. And I can show you that real quick. But of course, as I mentioned, the answers are in the PDF with the actual questions. So here are all the decimal translations of these numbers. Okay, right here in the document. And if you convert these numbers to binary, there they go. I did want to mention something about this last question where you were decoding. It decodes to binary space is not scary. The space is in here and there's an exclamation mark at the end. You will often see in people's company logos or their challenge coins, things like that. You'll often see a series of binary digits like this. If you group them into bytes, 8 digits, 8 bits, and you notice that all of the leading digits are 0, then chances are it is an ASCII encoding of some message like this. Because if you look at the ASCII table here, the largest number is 127. Now remember, this leading digit is the 128th place, right? So what that means, if all these are leading zeros, is that these numbers must translate to a number less than 128 because there's no 1 in any of the 128th places. And so, yeah, if you see a bunch of 8-bit values that have all leading zeros, chances are it's an ASCII encoding like this. And if you translate everything and do the lookups into this table, there'll be some sort of, hidden message or motto or something like that they want you to figure out. And sometimes you see that as like a capture the flag kind of quiz or something like that. But anyway, so ASCII is the way we encode letters as binary data. And there have been other such encodings over time. IBM created an encoding called EBCDIC for their mainframe computers back in the 1960s, extended binary coded decimal interchange codes. But ASCII, which you see here, is the one that won. And of course, ASCII, of course, has now been supplanted by Unicode, but the lowest Unicode code point is the ASCII English table. And then we basically extended ASCII to make Unicode for foreign character sets like kanji and things like that. Anyway, so now I did not, I will confess, do this question manually. You can find any number of binary to ASCII and ASCII to binary encoding sites out there on the internet. So you can, like I just literally typed in binary is not scary, hit the button, and it translated it to this binary encoding, which I then cut and paste into the slide. And similarly, if you have binary like this, you can find a site where you paste in the binary, hit go, and it just translates it into ASCII for you. So, again, it's fun to do this by hand a little bit, but if you're just trying to get through your day, there are websites available that will we'll do that. Yeah, and actually somebody's posted into the Discord chat a link to one such site. So plenty of those out there. Okay. We're going to go ahead and roll on into the next section, of course, here. Oops. Nope, not where I want to be. That's where I want to be. Okay, cool. So